So on here, you're matching these equations with these graphs. So for graph A, which one of these matches up? Okay, so that's an absolute value. And that's what these absolute value bars are. Okay, what about B? Which one? 1, C, 3, and then D. Okay, cool. So this is what we're going to talk about a little bit today. This is an exponential function because it has an x in the exponent. Okay, so again, we're going to talk about exponential functions. Okay, so on your paper, we're talking about exponential functions. And they have an x in the exponent. Okay, quadratics is what we talked about last unit. And that had a 2 in the exponent. And then we obviously already have talked about linear. So we'll reference that a little bit. Okay, so we're taking this piece of paper. How many sections do we have right now with this piece of paper with no fold? How many sections do we have? We have 1, right? Which is where we see it up here. Okay. Now, if we take it and we fold it into half, how many sections do we have? We have 2. Okay, so we see 1 fold equals 2 sections. And the expand function is 1 times 2, which is 2 to the first power. Okay, one thing I do want us to note is on here, it says 2 to the 0 power. Does everybody see that on their paper? So 2 to that 0 power, anything raised to the 0 power equals 1. Anything raised to the 0 power equals 1. I need you to know that for this unit, okay? Now, if we take our paper and we fold it again, so we folded it twice, how many sections do we have? We have 4, right? Okay, so filling in our table, we have 4 sections. And the way we expand that is we took 1 section times 2 sections times 2 sections. So what's 1 times 2 times 2? That's 4. We can also represent that as 2 raised to the second power. Everybody see it? Okay. If we take our paper and we fold it again, okay, how many sections are we going to have? 8 sections. So that means we're going to take 1 times 2 times 2 times 2. How many 2's do we have here? 3. So this is going to be 2 to the third power. Let me see where I got that from. Can you fill in the rest of this table? Okay. So what would be the next one? So 4 sections, or I'm sorry, 4 folds would be how many sections? 16. Yeah. Okay, so we would have 1 times 2 times 2 times 2 times 2, which is 2 to the 4th power, right? Okay. Now, what about 5? If we folded it 5 times, how many sections would we have? 32. Oh, I can't write this tiny. 1 times 2 times 2 times 2 times 2 times 2, which is 2 to the 5th power. Okay, what about 6 times? 64. And about 7 folds, it's kind of hard to fold those papers, right? Okay, so 1 times 2 times 2 times 2 times 2 times 2 times 2, and that's 2 to the 6th power. Okay, so how would we write x? Let's say that we wanted to fold it x number of times. We would say 2 to the x power. Everybody see that? Okay, so using your table and folded paper, what patterns do you notice? So look at our number of sections. What's going on here? Looking at our number of sections, what's happening there? They're what? Doubling, they're increasing. Okay, so we're doubling also known as multiplying times 2. Okay, using the pattern from the table, determine a mathematical model to represent the data. Okay, so with exponential functions, if you look up on the board, we see that we have this equation. Okay, so you have y equals a times b raised to the x. A is going to be our initial amount, and b is going to be our rate. So looking at our situation, what was our initial amount? How many sections did we start with? 1. So we've got y equals 1 times, what are we doing each time? Doubling. So we're going to say 2 raised to the x. Now, you're not going to see 1 times 2, because 1 times whatever's over here is whatever's over here. So we're going to actually shorten this to y equals 2 raised to the x. Okay. All right, so on number 5, it says folding a piece of paper into the sections is also known as an example of exponential function. Calculate and compare the rates of change over the intervals below. What do you notice about the average rate of change for the exponential function? Okay, so from 1 to 3. Let's have the conversation of average rate of change first. Okay, just a reminder, average rate of change is going to have this formula, y2 minus y1 over x2 minus x1. Okay, that's slope. It's just a fancy way of saying slope. Okay. The reason why we just start using this terminology is that in science, you're going to see it as rate of change. You're not going to see it as slope. Okay. So on here, we've got from 1 to 3. 1 is going to be our x1. 3 is going to be our x2. Now, how do we get our y1, y2? Well, we come up here to the table, and when x is 1, we look at what y is. When x is 3, we're going to look at what y is. So this is going to be your y1. This is going to be your y2. Okay, and so now we've got all the information and we're going to plug in. So that's going to give me 8 minus 2 over 3 minus 1. So 8 minus 2 is 6. 3 minus 1 is 2. And we know that 6 divided by 2 is going to give me 3. Okay. So our average rate of change for the interval from 1 to 3 is going to be 3. Can you try part B? Average rate of change does not go away. You always have it in science as well as in math. Okay, so take a moment, try the next one. I'm going to do this over to the side so you can actually like see it. So we've got from 4 to 6. So x1 is going to be 4, x2 is going to be 6. Okay, we're going to look at our table for 4, which is 16. And then for 6, which is 64. So we're going to plug in 64 minus 16 over 6 minus 4. And that's going to give us 48 in the top, 2 in the bottom. And 48 divided by 2 is 24. Okay, can you try part C? So I got 12.4, or you probably got like 12 and 2/5 or whatever, however you simplified it. If you left it as 62 over 5, that's fine too. All right, so which one's the biggest? A, B, or C? E. B has the biggest rate of change. Okay. Now, I was going to say it has the smallest interval, but that's not true. Okay, so you will always have an average rate of change question pop up. Okay, go ahead and flip over to the back. Now, imagine you were told to fold this sheet of paper in half and determine the area of one of the sections after you made the fold. Okay, so let's kind of have this conversation. If I told you the original paper had an area of 80, okay? And you fold this guy in half. That's 2 sections. What's the area of one of the sections? 40, okay? So, again, if we took a piece of paper, we divided it, and I said, hey, find the area of one of the sections, that would be 40, right? So that would take 80, we would multiply it times 1/2, or divide it by 2, and that would give us 40. What about on the next one? If I took the paper and I divided it into 4 sections, and I said, hey, find the area of this guy, you would tell me it is 20, and you would say, take 80, multiply it times 1/2, multiply it times 1/2 again. So that would be 80 times 1/2 raised to the second power. The reason why we got that second power is because there's 2 1/2s that we're multiplying by. What about on the next one? Well, that one would be 10. And we would take 80, multiply it times 1/2, times 1/2, times 1/2. And that would be 80 times 1/2 raised to the third. Can you fill in the rest? Exactly. So you should have gotten 5, 2.5, 1.25. And again, you would fill this in as 80 times 1/2 raised to the fourth, 80 times 1/2 raised to the fifth, 80 times 1/2 to the sixth. Now, our equation for this, our initial was 80, our rate was 1/2, and we're raising it to the x power. Okay, now in example A, so on the paper on the previous page, that was an example of a growth model. On the one on the back, that's an example of a decay model. Okay, so really quick, on the front, we had this equation. On the back, we had this equation. What's the difference of these two? Go ahead. One's a fraction. Okay. Anything else? Go ahead. One goes up, one goes down. So the front was growth. The back was decay. And Michaela just told us that this is a fraction. So in order to be growth, growth is going to be B is bigger than 1. Decay is going to be B is less than 1. Okay, so in our own words, describe what growth means. That means that our B is bigger than 1, decay is less than 1. And what do I mean by B? Well, remember our equation that we learned at the very beginning? Our B is our rate. Okay, so if that rate is bigger than 1, it's growth. If the rate is less than 1, it's decay. Okay, so again, we're going to summarize that really quick. Okay, so growth is B is greater than 1. Decay is less than 1. And we learned that the equation is A times B raised to the X. Okay. I need you to know that formula, y equals A times B raised to the X. That's going to come in handy. Okay. You also got to know growth and decay. You not only use that for my class, but you also use it for science classes. So you'll use it in bio, you'll use it in chemistry, and you'll use it in physics. Okay. A lot of you asked me what ratio meant on the final exam, and I couldn't answer it when you were taking the test. But ratio just means that you're multiplying by a constant. You're multiplying by a fraction or a whole number. Okay. Now, looking at our table, when you are given a table, you're only going to be given these 2 columns. You're not going to have 4 sections of columns. Okay. So looking at these first 2, we see that from here to here, we multiplied by 2. We're multiplying by 2 each time, right? Okay, and we see that there. We talked about the decay, and we see that what's happening here is we're multiplying by 1/2. Okay, another way to say this is you're dividing by 2, but we always want to put it in terms of multiplication. So multiply by 1/2 is the exact same thing as dividing by 2. Okay, I want you to take a moment. You're going to complete these 3 questions. It says a researcher is curious about the spread of the Spanish flu in 1918. A records book from the hospital contained the following table. This table will allow the researcher to predict how many patients would have contracted the Spanish flu by day 100. So using the table, answer these 2 questions. This is you notice it's happening to the number of people infected with Spanish flu. Increasing by how much? Like what's happening each time? We're multiplying by 3, right? And then determine the exponential equation. So how much were we starting with? 1, and how much are we multiplying by? 3. And normally we leave off this 1. So we're going to say y equals 3 to the x. Okay. Now it says figure out how much there is after day 100. So that means that we're going to plug in 100 in for x. Okay. Now, when you type this for calculator, you're going to get something a little crazy. So if I type 3 to the 100th power, you get this. This says times 10 raised to the 47th power. That means take your decimal and move it 47 times this way, and then fill in zeros all the way through. So how many people is that? That's a ton. That's like basically the entire population, right? Now, not all flus and things work like that, but it is a very big number. That's why we had our lockdown during COVID, right? Because if you spread it to 3 people and then you continuously do that, then it became a problem. Okay. Go ahead and take a look at the next set of notes, next page. So it looks like this. Okay. Go ahead and answer these 3 questions. So draw what happens in hour 2, draw what happens in hour 3, and then what patterns do you, because I feel like you can get this. All right. What happens in hour 2? Well, these are splitting into 3s. Okay, so that means that each one of these splits into 3. So this one splits into 3. This one splits into 3. This one splits into 3. So how many do we got? We got 9, right? Now in hour 3, each one of these splits into 3. So this is going to look like this. How many do we have in total? My awesome bacterium. What's 9 times 3? 27. Okay, so in the first hour, or I'm sorry, in the second hour, we got 9. In the third hour, we got 27. So what are we noticing? What are we multiplying by? Multiplying by 3. Questions? So before I was a math major, I was a chem major. And my first or second lab that we did, we literally had to draw bacteria. And it was talking about it splitting. Okay, so this comes back up even in college. Okay, now it's not this easy, but that was my first lab. Okay, so go ahead and take a look at the paper that says multiplying microbes. Okay, so what you're going to do is this is kind of like a continuation of what we just talked about. Okay, so you're going to fill in this top part, and then you're going to come check in with me, and then we're going to graph it. Okay, I know that a lot of us struggle with graphing, so I definitely want to hit that today. The table, the equation, and the graph all say the same thing. All it's doing is rewriting it in a different format. Okay, so you're going to complete the top section, come check in with me, and then you're going to complete the bottom section. You can work with a partner, but you need to complete this. Okay, don't sit there and not get anything done. Okay, notes. So you should have filled in this table, and it should have been 500, 1,000, 2,000, 4,000. So is the growth of the bacteria characterized by common differences or common factors? Here's 2 vocab words that you're going to see often. What is the word difference mean in math? Subtraction. And what does the word factor mean in math? If I say find 2 factors of something, multiplication. Okay. So are we multiplying or are we subtracting? We're multiplying. Okay, so we're multiplying when we're doing all this, right? Okay, so what does the 500 represent in the problem? The initial amount, right? Ooh. And that's the initial amount. Okay. And how were you able to find our 6? What equation did you use? You should have done 500 times 2 raised to the x, and you plugged in 6, right? Or you plugged in p. When they asked for p in that bottom part, what they were asking you to do was say 500 times 2 raised to t power. That's all they were trying to say. Okay, now one thing I do want us to note, and something that I think we struggle with, is that we don't see the table, the equation, and the graph being the same thing, but they are. Okay, so even though this table has just a bunch of numbers, it relates to the graph. This 0, 500 is this first point right here. This 1, 1,000 is right here. Are you looking for Joyce? She's running a couple errands, so she's around the school. And then 2, 2,000 is right here, and then 3, 4,000 is right here. Okay, and we can see that by, if we plugged in 1 into this equation, we would get 1,000. Right? So what I'd like for you to do, oh, sorry, this is still my part. What is a reasonable domain for the given function? So domain is going to come from this section right here, this hour. Okay, so what is our lowest domain value? 0. Now, how far does this go? It could go to 6. Could it continue on? Yeah. Could be for infinity, but like that would kind of be horrible as a researcher, right? But it could go past this table. Let's say that we go all the way to 24 hours. Now, it didn't specify when we stopped looking at this, but looking at bacteria for about 24 hours is not a bad thing, right? We could do that. Okay. What about the range? Well, using our x values, what was our lowest y value? What was our lowest y value? 500. How would we find our highest y value? Well, you told me that we're going to observe for 24 hours. So we're going to take 24 and we're going to plug it into our equation. Okay. And when you type that into your calculator, so I hate doing this on an iPhone. If we say 2 raised to the 24th power, 2 raised to the 24th power, and then we multiply it times 500, we're going to get this number right here. Which is 8,388,608,000. So in 24 hours, that's how many bacteria would grow based off of this information. Oh, yeah. Yeah. That's why you should clean your house, people. That always works. Okay. Now, again, this is just looking at one day. It could go past. Not you hand sanitizing. I'm dead. Okay. Go ahead and take a moment. Check yourself. Try this problem. Answer these 3 questions. Fill in this table. Okay, this tells me, do you understand what's going on? You should have had 1,000 for the first thing, doubling each time, and then writing this equation would be 1,000 times 2 raised to the x. After today, you should be able to write the equation and then tell me what the initial and the rate are. If you can do that, then you're on track. Okay, last question. Go ahead and look at that next section. A group of biologists is surveying mice population in a forest. Here's the equation. It gives the total number of mice, the year since the survey began. Explain what the numbers 75 and 3 mean in this situation. This question is on your test. It is also going to be on your intro. It will also be on your final exam. Obviously, not the exact same wording, but the same type of question. So what does that 75 represent? The initial. 75 represents the initial amount of mice, right? So 75 represents the initial amount of mice. Okay. And then 3, what does that represent? What does that 3 represent? We call that the rate. Okay, so how much they're going up by each year. Does that make sense? Okay, there's a question on your test that's just like that. Make it be easy because it really is. Okay. Once you're done, you're going to look at the paper that says who went viral. So explain to me, what does it mean to say that something is going viral? What does that mean? What does it mean by going viral? A lot of likes, a lot of views, maybe? Define a lot. Because, like, you know, 100,000 is going viral. Okay. Okay, makes sense. Okay, so you've got these 3 tables, and Sam and Justice and Antonella each created a video on different social media platforms that they wanted to go viral. As soon as they uploaded their content, they immediately shared it with 10 friends. So they all started with 10, okay? Your job is to fill in this chart, okay, based off of the pattern that's happening. Now, I do want to clarify, these are not all exponential. They're not all exponential. There's 3 different types of equations and functions that we talked about. We talked about linear, that has a constant first difference. We talked about quadratic, which has a constant second difference. And then we talked about exponential today, and that's going to deal with multiplication. Okay, so as you're going through these, they're not all exponential. They're not all multiplying by the same thing. Your job is to figure out which one is which and how to fill in this little box down at the bottom. Once you do that, you're going to flip over to the back and you're going to answer those questions. Okay, so go ahead and take a moment. You're working on those.